Hello everyone. So we can continue our chapter 28, radioactivity. So today we start with the topic half-life. Now the definition for half-life. The time interval in which mass of a radioactive substance, mass of a radioactive substance or the number of its atoms is reduced to half its initial value is called half-life of that substance. It is denoted by the letter T. That is, here half-life means what? If we take a radioactive substance of 100 gram. Consider that we have taken a radioactive substance of 100 gram. The time taken to make that 100 gram of radioactive substance to half of it, that is 50 gram. That is that 100 gram radioactive substance after its radioactive process, that is spontaneous emission of rays, when it becomes to 50 gram, from 100 to 50 gram, what is the time taken there? That time interval we call it as what? Half-life of a substance. Clear? So in which mass of a radioactive substance becomes half, or number of atoms becomes half of it. So that time interval we call it as half-life, and it is denoted by the letter T because it is given in your text. We can use T half also. Clear? T half, small letter T subscript half, or capital letter T subscript half. Then next is relation between half-life and decay constant. Now what is this decay constant? In the previous class we have seen, right? We have seen Rutherford-Saudy's law, right? N is equal to N0 e raised to minus lambda T, where that lambda refers to decay constant. So now we are going to find out a relation between half-life and decay constant. So we are starting this relation, or we are deriving this relation starting from Rutherford-Saudy law, that is N is equal to N0 e raised to minus lambda T. Clear? Now how to find out the relation? We are assuming the condition, right? That now T half has reached. So when T half has reached means what and all changes will be there? Time will be changed to T half, and number of atoms present will become half of it. So if N0 atoms were present initially, now what is the number of atoms present? N is equal to N0 by 2. Clear? Initially there was N0 atoms and time was 0. Now after T half, what happened? The N became N0 by 2. So in the first equation we are substituting for N as N0 by 2 and for T as T half. Now when we substitute, we can see N0 on both sides. We can strike it off, right? Then what will be left out? 1 by 2 is equal to e raised to minus lambda T half. Clear? 1 by 2 e raised to minus lambda T half. Now this e raised to minus lambda T half, how we can write? We can write it as 1 by. Since that minus sign is there, we can make it as 1 by. So on both sides, how it will become? 1 by 2 is equal to 1 by e raised to lambda T. Now just bring it to opposite sides. That is e raised to lambda T on one side and on another side 2. Clear? So what it will become? 2 is equal to e raised to lambda T. Now take log on both sides. So log to the base e 2 is equal to lambda T, because when we take log, exponential will go. So log to the base e2 is equal to lambda T half. Now log to the base e2 is what? Its value is 0.6931 is equal to lambda t half. So from there we can write the relation for t half. T half is equal to 0.6931 by lambda. I think it is clear. Now here a graphical representation of decay of a radioactive substance is shown. The number of, on the y-axis you can see number of undecayed nuclei at a time, and on x-axis time is given. So we can start from n0. As t half becomes, it becomes to suddenly it falls. Then the process for the first half life, the radioactive disintegration process is fast. Then from first half life to the next half life, the process becomes slow. Again it becomes slower and slower, right? So actually this disintegration or decay takes a longer time, right? It takes a longer time to reduce or become invisible. That means to fully decay off. Clear? So that graph is given there. Now how to say in numbers? If we say, if we have taken 100 gram, right? They have said 100. So 100 to become 50. Very fastly 100 will become 50. Very short period of time needed. Then that 50 to become 25 takes a little more time. Now that 25 to become 12.5, half of it will take a little more longer time, right? Likewise, it goes on. Now next topic is activity of a radioactive substance. What do you mean by this activity? Activity is the rate of decay of a radioactive substance. The rate of decay of a radioactive substance is called activity. So we can write as equation what R is equal to minus dN by dt. Or we can say dN by dt is directly proportional to N. The rate of decay of radioactive substances proportional to N, right? That is from Rutherford-Saudy's law. Then next is from these two, right? So R is equal to minus dN by dt according to activity of a radioactive substance. And from Rutherford-Saudy law, minus dN by dt is directly proportional to N. We can compare or we can combine them together. What we can write? We can write it as activity is directly proportional to number of atoms left at that instant. Clear? So, activity of a substance at any instant is proportional to number of its atoms left at that instant. So now, in order to find out how many half-lives are there, right? Or how many number of atoms are present after half-lives, 2 or 3 half-lives. In order to calculate that, we have derived an equation. You can see at time t equal to 0. That is initial case. Initially, we are taking time, let it be 0, and n becomes n0. Then after t half we can represent it as t half or capital T. So what will become to n? N will become n0 by 2. So now we can see 2-3 steps. Just go through the steps. N is equal to n0 by 2. T is equal to T, capital T. That means during first half life. N will become 2. N is equal to 1 by 2 raised to 1. Now after 2 half life, that is t is equal to 2t, capital 2t. Then what will become to n? N will become n0 by 4, or we can rearrange and write it as n0 into 1 by 2 whole raised to 2. Similarly, if 3 half-lives are completed, then we can find out the number at that instant by n0 by 8. So we can rearrange and write n0 into 1 by 2 whole raised to cube. Now if we check all these equation, a pattern is being followed, right? So we can say after n half-lives, right? After n half-lives, that is Generalizing, if after n half-lives, number of atoms present will be equal to n is equal to n0 1 by 2 whole raised to n, where n means number of half-lives. So that shaded part, the shaded equation is important. We have to do numericals based on that. This is the relation from which we can find out the number of atoms present at that instant and also how many half-lives have completed. Then next is mean life or average life of a radioactive substance. What is mean life or average life? The average of the lives of all atoms in a radioactive substance. The average of the lives of all atoms in a radioactive substance is called mean life or average life of that substance, and it is denoted by tau. We know how to write tau, right? So here the mean life is denoted by tau, and this tau is also, that is mean life is actually equal to reciprocal of decay constant. So we can see the equation there. Tau is equal to 1 by lambda, or tau is equal to T by 0.6931, that is equal to 1.443 T. So these two equations we can write it for mean life or average life. The next is some of the units of radioactivity. 3 units are used. Becquerel is the first one. It is actually, becquerel is given as a remembrance or to honor whom? Henry Becquerel, right? He was the person who started or who introduced what? Radioactivity. So to honor him, we have given the unit name as Becquerel. So Becquerel is the SI unit of radioactivity, and it is defined as 1 disintegration per second. That 1 disintegration per second is written in the short form 1 dps. Then next is Curie. Curie. Curie is defined as quantity of radioactive material in which number of nuclear disintegration per second is same as 1 gram of radium. So here 1 Curie is actually somewhat equal to activity of 1 gram of radium. So we can write as what? 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. Clear? 10 raised to 10 becquerel, or 10 raised to 10 dps. Now specific activity is defined as disintegration rate per unit mass. Disintegration rate per unit mass of radioactive substance. So now by this the portions or the topics in that section gets over. So thank you all.